I started.
So when we had y equals x squared, and we would write either y prime or dy dx equals, we said that dy dx meant the rate of change of y with respect to x, right? So if we look at number 1 now, where we have this thing, this 100 cubic centimeters per second that we say is the rate of change of volume with respect to time, how are we gonna, like, what mathematical expression can we use? If dy dx means the rate of change of y with respect to x, how are we going to write the rate of change of volume with respect to time? This is where you guys come in.
Wouldn't it be 100 centimeters cube squared
Well, it is 100
equals?
cubic centimeters per second, right? I want to know how to label this. What is it what mathematical, like, I don't want to have to write rate of change of volume of the balloon with respect to time equals 100 cubic centimeters per second. I want to have a symbol that means all these words. Okay? And I gave you guys this because they're analogous to each other.
Oh, so dy over dx?
Well, dy over dx means the rate of change of y with respect to x. I want the rate of change of volume with respect to time.
dv over dt?
dv over dt.
What do you say?
dv over dt.
dv over dt would be the rate of change of v with respect to time, right? dv dt would be the rate of change of volume with respect to time. Okay, so that cubic centimeters per second, that units on that, first of all, needs to say to you rate of change. The cubic centimeters, when it says volume over seconds time, then you need to understand that that's representing the rate of change of volume with respect to time. Okay, what's my unknown on this one? Okay. I want to know how fast is the radius of the balloon increasing? I want time. Time will tell me how fast it's increasing. My radius is increasing. Okay, the rate of change of the volume of the balloon with respect to time is represented by a dv dt. What am I asking for the rate of change of? The radius. Okay. And I want to know how fast it is, so I want the rate of change of the radius with respect to time. So I'm going to write that how?
dr over dt?
There you go. So that's my unknown. Okay, dr over dt is my unknown. Okay. All right. For number 2, we've got this lovely 10-foot ladder here, propped up against the wall. That wasn't an embarrassing question. Okay. All right, so our ladder's resting against the wall, the bottom slides away. I just want to go through the key points on each problem so you guys can see how things are similar, that maybe it won't be as overwhelming to you guys. So for number 2, I've got a 10-foot ladder resting against the wall. The bottom is sliding away from the wall at 1 foot per second. So this is sliding away at 1 foot per second. And I want to know how fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall. So my variables for number 1, my volume and my radius were both changing, right? What's changing on this ladder situation? Which distances?
X distance.
What are you calling x right now?
The wall to the end of the ladder.
From wall to ladder, we'll call that x. And then what other distance is changing?
Y.
Wall to floor, top of the ladder to the floor, which I'll call y. Okay? So this 1 foot per second, is it a measure or is it a rate of change?
Rate of change.
It's got to be a rate of change because it's foot per second, right? Okay. What is it the rate of change of?
The ladder sliding off the wall.
Which distance
Oh,
is it the rate of change of? The x distance or the y distance?
the x distance.
The x distance, because it's sliding, the base of the ladder is sliding further away from the wall, which means that x value, that distance is going to increase. So dx dt is how I write the rate of change of x with respect to time. Is the value of x going to increase or decrease as my ladder falls? The value of x is going to increase. The base of the ladder is going to move further and further and further from the wall. Okay? Is my y value going to increase or decrease as I go?
Decrease.
It's going to decrease because the top of the ladder is sliding towards the floor, so the distance from top to floor is going to decrease. What's my unknown for this one when I ask how fast is the top of the ladder sliding down the wall? A dy over dt, the rate of change of that y value with respect to time. And you guys just told me that this value has to be
Negative.
negative. Alright, so it will be negative because why?
Because the distance is getting smaller.
Yeah, because the distance will decrease. The distance, I'll be specific, between the top of the ladder and the floor is going to decrease. Okay. All right. Let's look at number 3 real quick. Let's talk about what we're given and what we need to figure out. So for number 3, I have a water tank with the shape of an inverted circular cone, which means this shape. Okay, it says it has a base radius of 2 meters and height 4 meters, so that means that this distance is 2 meters. Oops. And that the whole distance of the whole thing is 4 meters. Sorry, the whole height of the entire container is 4 meters. Okay. Alright, it says that water is being pumped in at a rate of 2 cubic meters per minute. Is this a measure or a rate of change?
Rate of change.
It's a rate of change because it's per minute. What are the units on cubic meters for? Volume. So it's change in volume over time.
Mhm.
How do I write that?
dV over dt.
dV over dt. Okay, and I want to know what my unknown is. Okay, it says to find the rate at which the water level is rising at a particular moment. So what am I looking for the rate of change of? The height of the water. So if I'm talking about the rate of change of height, how should I call that?
X.
I'm going to say dt for height. Okay, if you prefer y, I just said we're going to come up with formulas in a second to relate our variables. And the formula for the volume of cone is going to involve an r and an h. So I'm going to use each for this one, but it really doesn't matter what variable you use as long as you're consistent. Okay. For number 4, we've got this dude walking along a path. Okay. There he is. He's walking along a path. He's gonna walk this way. And there's a searchlight that's pointed at him. And initially it's shining on him when but as he moves, it's going to continue to shine at and point at him. Okay, so it's going to rotate. Is there anything that's a constant value in this mix? Okay, the rate at which he's walking, that's the rate of change of what, guys? Where is the man walking? He's walking this way. Okay. This is the point on the path closest to the searchlight, right? So he's moving away from that point. I just don't know what to label here. You tell me. What do I label? Where? Here? We'll call this distance x. Okay. And then somebody did a vertical thing in the air for me. What is this distance? 20. Does the searchlight ever move?
No.
No, that's a constant. Okay, the searchlight's not going to get up and walk to a different position. It's just going to rotate to follow. So it's at a fixed point 20 feet from where this guy started. Okay. What else is changing here?
Direction.
Okay, so
Distance.
I'm rotating. So what's changing?
Your angle?
The angle. Yeah, this little angle in here is changing.
It's a triangle.
Do I have a triangle? Oh my goodness. So for number 4, it says a man walks along a straight path at a feet of 4 feet per second. Sorry, at a rate of 4 feet per second. What can I label with 4 feet per second here? Now 4 feet per second, is that a measure or a rate of change?
Rate of change.
Rate of change. The rate of change of what? Which distance?
The man from point A to point
Okay, so what are we calling a distance?
Dx over.
X, so it's going to be a dx dt. So dx dt is this. And I want to know how fast the searchlight is rotating. At what rate is the searchlight rotating? So what's my unknown? The rate of change of what?
Theta.
Theta. So d theta d t, right? The rate of change of theta with respect to time. The rate of change of the angle with respect to time. That's my unknown. Okay. Alright, I'm just gonna go back and make some room here and rewrite what we had labeled. And I've got my spherical balloon. Okay, we said that dV dt is 100 cubic centimeters per second. And our unknown was our dr dt. Okay. Okay. Once you know what your known and your unknown are, you need to come up with an equation that relates those variables. So when you guys have a volume or an area, it's pretty straightforward. I'm talking about the volume of what here?
The balloon.
The volume of the spherical balloon. And you guys probably don't remember this, but the formula for volume of a spherical balloon is 4/3 pi r cubed. Okay. What was like the category that we used for the dV dt and the dr dt? Those are what types of measures? Somebody mumbled it. Rates of change. They're rates of change, right? How do I go from values to rates of change? Is it cutting me off?
No, there's just a glare. And now the screen's purple.
How do I go from a function to a rate of change? How do I go from a function to a rate of change in your calculus class? You
Derivative.
take a derivative. Okay, so now, if we did derivatives the way that we were doing derivatives like normally, if I had y equals x squared, I would write y equals x squared, y prime equals 2x, or dy dx equals 2x. It's the rate of change of y with respect to x. So if I had v equals 4/3 pi r cubed, and I were to take a normal derivative, I would say that v prime would be what's the 4/3 pi here? It's a coefficient, so I'm gonna hold it. And the derivative of r cubed would be 3r squared.
Yeah.
If this y prime is the same as a dy dx, what is this v prime the same as the way that I've done this?
dv over dt.
dv over d
R.
r. It's the rate of change of volume with respect to my radius. I don't want this. Okay, this is not good for us. I don't want dv dr. I want dv dt. I want the rate of change with respect to time. I want to know how fast things are changing at a particular moment. Okay? So what we're going to have to do, because this does not work for us, what we're going to have to do is we're going to have to take all derivatives implicitly with respect to time. Alright, we're going to take all derivatives implicitly with respect to time. I had somebody to edit this video for me later. Okay. Which means anytime I take the derivative of any variable, I gotta be like, yo, hey. I'm getting attention from all of it. I just took the derivative of this variable with respect to time. So the derivative of v is just a 1, but hey, I just took the derivative of v with respect to time. If you're taking, right, do you guys see that there's no t in this mix whatsoever?
Mhm.
It's weird that it's being inserted, so I have to forcefully insert it by taking all derivatives implicitly with respect to time. Okay. The 4/3 pi is still a coefficient, I'm gonna still hold it. The derivative of r cubed is still 3r squared, but hey, I just took the derivative of r with respect to time. Okay, and that's how my derivatives are gonna look. So I'm gonna take the derivative of every variable implicitly with respect to time. Okay. Let's look at number 2. Oh, I didn't write equations for these. Okay, that's okay. For number 2, I need an equation that relates my variables. What equation can I use here? I need an equation that relates x and y that will always hold true for this triangle.
Pythagorean theorem.
Pythagorean theorem. Pythagorean theorem will work. Right? It's a right triangle. So I'd have x squared plus y squared equals r squared. H squared. Can I put the 10 in?
Yeah.
Why is it okay to put the 10 in?
It's always going to equal 10.
Because it's not changing. Okay, if something is going to always be constant, you can leave it that way. Okay, if something is changing throughout, like the volume is always changing, the radius is always changing, it's asking me to freeze it at a moment when the diameter is 50. We'll get back to that in a second. Okay, but everything's always changing. Here, my x is changing, my y is changing, that 10 is not changing, so it's okay to throw that in right away. Okay. Girls, there's worksheets for you somewhere. Okay, I'm going to take this derivative with respect to time. So the derivative of x squared is what? 2x? 2x what? Hey, I just did the derivative of x with respect to time.
Dx over dt.
Plus, what's the derivative of y squared?
2y.
2y, hey! Yeah, I need to say that I just took this derivative with respect to time. What's the derivative of 10 squared? 0, right? The derivative of 100 is 0. Is that consistent with what we've said?
Yeah.
How is that consistent with what we've said? What'd you guys tell me about the ladder?
It's getting closer and closer to the ground.
No. What does the 0 on this represent?
Oh, that's the constant. Its height is not going to change.
That the ladder itself, the length of the ladder, is not changing. Okay? I'm acknowledging that the distance from the base of the ladder to the wall is changing. I'm acknowledging that the distance from the top of the ladder to the floor is changing. But the length of the ladder is not changing, so its rate of change is a 0. Okay? Okay. 3 I actually want to skip for right now. I'm going to look at number 4 with you guys. We'll come back to 3 tomorrow. Okay. For this one, I have an angle and a side. How do I relate an angle to a side?
So good to
Some trig, right?
Yeah.
Some trig up here? Okay. Alright. If I take sine of theta, what would sine of theta be?
X over.
X over my hypotenuse? Is that good for us or no good for us?
No.
That's not good. Why is that not good?
Because we want the.
Well, x is a variable that I have some information about. Do I know anything about the hypotenuse?
No.
Okay, I know nothing about this. So that's not a good one for this particular problem. Okay? What about cosine theta? Cosine theta would be what? Here's theta. Cosine would be
X over 20.
no
20 over
20 over the hypotenuse. Again, not a good one because I know nothing about that hypotenuse. I don't know its length. I don't know its rate of change. I know nothing about the hypotenuse. What about tangent theta? Tangent theta is going to be a little bit better because what's tangent theta?
X over 20.
X over 20, and it involves the side that the variable side that I know a lot about. It involves my constant side, and this is going to be something I can work with. Okay. When you guys have an angle involved, you're going to need trig. Okay. You're gonna have to pick the trig based on the information that you're given. So sometimes sine's gonna work, sometimes cosine's gonna work. Excuse me, sometimes tangent's gonna work. It's all about the particular situation. Okay, you guys are with me? Okay. Excuse me. All right, can I take the derivative of this? We're gonna write it over here. What's the derivative of tangent theta? Secant squared of theta. Hey! What goes there?
Theta over dt.
D theta dt, good. Equals the derivative of x over 20. That's just like a 1/20th x. What's the derivative of 1/20th x? 1/20th. Hey! dx. Okay. Alright. So no two problems are going to be exactly the same, but you guys see how there's like a lot of similarities. You can pull out a lot of things based on units, what things are. Okay, which is why I love our units on these problems. Okay, you need an equation to relate the pieces. When you take its derivative, you do it implicitly. Once you've taken the derivative implicitly, it's all about plugging in what you know and solving for what you know. Okay, so dv dt we have labeled as 100. My 3's can divide out. And I have 4 pi times r squared. The r dt is my unknown, so I want to keep that in there. But I'm going to put in an r here. What can I put in for r?
D over 2.
Okay, what's d? 50, d is 50, right? When diameter is 50, that means r is 25. So at the particular moment that I want to be freezing time to figure out the rate of change of my radius with respect to time, I want my radius to be 25. Okay? And then I'm just going to solve for dr dt. I'm going to do a 100 divided by all that crap. So 4 pi times 25 times 25. That'll equal dr dt. I'm writing that out because I'm lazy in terms of finding a calculator. Okay? And 4 times 25 is 100. So I end up with 1 over 25 pi. What are my units? Make sure your pi is in the denominator, guys. It's 1 over 25 pi. What are the units on this dr dt? The units on dv dt are cubic centimeters per second because it was volume over time.
Centimeters per second?
Good. So it's my radius, if my volume is measured in cubic centimeters, my radius is measured in centimeters, but it's a rate of change of it, so it's centimeters per second. Okay? So there's my dr dt. We look at number 2. Okay, plug and chug with what I've got. I said that we have a 10-foot ladder, the bottom's sliding away. How fast is the top of the ladder sliding down the wall? When the bottom is 6 feet from the wall. So when what? What is 6 feet? X, good. Okay, so I'm going to plug and chug and solve for my dy dt we said was my unknown. So I'll have 2 times 6 times dx dt was what again? 1 plus 2 times y. I'm not sure about what y is, but I'll figure out in a second. The dy dt is my unknown. That's supposed to be there. Okay. How do I figure out what y is at this moment? Yeah, Pythagorean theorem for right when this side is 10 and this side is 6. What's this side? 8, right? Because 3, 4, 5 triangle. Okay, or you could do Pythagorean theorem to find 8 for that missing side, so I put an 8 here. And I'm just going to solve for dy dt. So I get a 12 plus u 16 dy dt equals 0. I'm going to subtract the 12 to the other side. So I'll get 16 dy dt equals negative 12, and then I'll divide both sides by 16. And that'll reduce to negative 3/4. The units on dx dt were feet per second. What are the units on dy dt going to be? Also feet per second? Do you guys agree or disagree?
Yeah.
Agree?
Because it's still length.
It's still the rate of change of a length. Okay, so it's still feet per second. Now, something minor that can trip you up either in a textbook answer or if it was multiple choice, is that the wording that I used on here is I asked how fast is the top of the ladder sliding down? Okay, what does the down imply?
Negative.
The negative. Okay? So dy dt, I'm going to just write it here, even though it has nothing to do with this. Dy dt is negative 3/4 feet per second, but the answer to the question is that the ladder is sliding down. And the down implies the negative at 3/4 of a foot per second. When you say that it's down at a negative rate, it actually implies that it's going up. It's a double negative situation that you just have to be careful for with wording. Okay, if it just asked you how fast is the length between the top of the ladder and the base of the wall changing, then you would say a negative 3/4, but because it says how fast is it sliding down the wall, the down has that negative in it. Okay. We'll just finish this one and then I'll set you guys off on your homework. Great. So for this one, I have that tangent theta equals x over 20. We took our derivative. We got secant squared theta. Hey, I took the derivative theta with respect to time. Is equal to the derivative x over 20 is 1 over 20. Hey, I took the derivative x with respect to time. Okay. Dx dt is supposed to be a 4, so I know that this is a 4. Okay. D theta dt, that's my unknown. But I need to know what secant of theta is so that I can square it and put it there. Secant theta is 1 over cosine theta, which means instead of it being adjacent over hypotenuse, it's hypotenuse over adjacent. Do you guys agree? Okay. And I'm talking about this triangle, where this side is always 20. When the top side, x, when the man is 15 feet from the point on the path closest to the searchlight, so when this is 15. Okay. I need to know what the missing piece is. Can I figure it out?
Yeah.
Yeah. Pythagorean theorem, or it's another 3, 4, 5 triangle. This is 3 times 5. This is 4 times 5. So this one would have to be 5 times 5. Or 25. Okay. So if I do hypotenuse over adjacent, I get 25 over, here's my angle theta, 25 over 20, which reduces to 5/4. Okay? So I'm going to put in a 5/4 here. So 5/4 squared times d theta dt is equal to 4 over 20 is 1 over 5. Right? And then to get rid of a 5/4 quantity squared, I'm going to multiply by 4/5 quantity squared. And so I'll get d theta dt is equal to, I'll have 4 squared on top, which is 16, and 5 cubed on bottom, right? 5 times 5 squared is 5 cubed, or 125. Okay. The units on this, because it's the rate of change of an angle measure, it's a weird one. It's actually in radians per second, the way that we did this calculation. Okay. Do you guys have any big questions? Okay, so again, it's this concept that things are all changing, but we can freeze it at a moment and consider that particular situation by taking the derivatives with respect to time. So we have our situation, or our equation that relates all our variables. When we take its derivative with respect to time, it's saying, okay, we understand that everything is changing. And so when I put it in, I can say, okay, well, at this particular moment with these particular measures, what's my rate of change? All right.